All right. Everybody, my name is Luke Miller, and I'm going to give a seminar right now. We're slotted for 4 weeks. Maybe we'll add some more as we go. What this is basics of quantum computing. We're not going to get super math heavy. I would love to geek out to you guys about all the linear algebra stuff behind this outside the seminar, but we're going to get some vocabulary down in this first session. And it's going to be more about the practice of what quantum AI is going to look like, what quantum graph neural networks is going to look like. Okay. There we go. So we're going to have 4 sessions right now. The first one's just going to be quantum fundamentals. Then we're going to talk about some of the key algorithms behind quantum computing, as well as what we're doing with quantum computing and AI. The third session is going to be primarily focused on quantum ML and what that looks like. That's where I'll be sharing a Jupyter notebook with what this material looks like. And then for the 4th session, because I'm a graph nerd, we're going to do graph neural networks. All right. So far, we're scheduled every 2 weeks at 10 a.m. Expect this to be about 30 to 40 minutes, 20 minutes of that I'll lecture, and then we'll just talk. All right. So today, we're going to just get the quantum computing fundamentals down. I just want us to have the same vocabulary. And so that we can start covering this, we'll talk about what is quantum computing versus classical computing, bits versus qubits. We'll move on a little bit to talk about superposition and entanglement, as well as some of the basic quantum gates. So what are the corollaries of and not gates for the quantum world? Come on in. And then I'll start talking about what the power of quantum has to apply to AI. So recently we've had IBM and others come out with quantum computers over 1,000 qubits. So we're really progressing. It was a few years ago we were really proud of a dozen. Okay. Now, quantum computing works in a fundamentally different way. Whenever we talk about parallelism and classical computing, we have separate processors doing separate processes and then merging them. In quantum computing, we are actually parallel processing material on the same device. So how do these quantum computers work? All right. So the way these quantum computers work is through various paradigms. So you have ion traps, where basically we trap an ion and then we perform operations on it to induce its spin, to change its spin, to put it in superposition. We also have superconducting quantum computers and photonic quantum computers. Now, any physics people in here, I'd love to hear more from you on how this works. So far, I've been focused on the computing side. But each one of these different types of computers has various strengths to offer, whether how long they're coherent or what the number of qubits that we're able to have. Okay. The relevance to AI, what we're able to do with quantum computing that's really, really interesting is right now, if you know anything about AI, basically we start with a random bunch of numbers, and we see how that is, and then we change our numbers, and we see how that is. We just do that a few thousand times, with gradient descent, try to get there. Quantum computers have the potential to test all values at once. All right, through superposition, which we're going to get into a bit, but with that potential that we can test all of these values at once. All right, now, this took me forever to accept. I don't expect you to accept it right now. But, in the early 1900s, we were using electricity, but we didn't really understand what it was or how it worked. Okay, now, with these quantum principles, we know it works. We know superposition works, we know entanglement works. But from your classical mindset and the physics we're used to, you're violating locality. You just have things that are completely seemingly disconnected that are operating together. They're entangled, they're doing things. Things are simultaneously in 2 separate states. Something is simultaneously on and off and every variation in between. Okay, so the elephant in the room is that these principles work. How and why they work? The best physicists in the world are working on that still. So, all right. So, all right. The primary thing we need to know is the qubit, the quantum bit. So with a classical bit, it's deterministic and binary. It is either 0 or 1, and we do them sequentially. We process them sequentially. The qubit all right, is determined based on typically the spin of a quantum particle. And it can exist in a state of both 0 and 1 at the same time through a process known as superposition. Okay, and we're going to describe that state as this psi here. All right, and you're going to have those alpha and beta are complex probabilities. So they're going to be that this particle is in a state of probability alpha of being in state 0 and probability beta in state 1. Now, if anybody's heard about Schrodinger's cat, once we actually observe this, once we make a measurement, it's no longer the superposition. It collapses to one of those. All right. Now, how do we determine that probability of the state that it's in? We repeat it. And we start seeing what that is. Hey, how often is in this state? How often is that state? All right. So this enables our parallelism. Whenever we have a state that's in superposition between 0 and 1, we're able to test multiple values at a time whenever we're doing computation. Now, here on the right side, you'll see the block sphere. This is the standard way of visualizing a qubit. Okay, a qubit exists somewhere on the sphere, where at the North Pole, it's purely in state 0. The South Pole is purely in state 1. All right, and then we have the positive ket, that's what the symbol is, the negative ket, the negative I, and the positive I. All right, now, whenever you get into multiple qubits, we don't get to have this nice, pretty sphere anymore. But as we move on, I'll start talking about things like phase and amplitude. It's going to be different feel how I visualize it in my head with this block sphere. Okay, how is my point on the sphere moving as I apply operations to it? Now, that's superposition. Entanglement, we can do operations that entangle two qubits. Okay, to where the state of one affects the state of the other. And that enables some things like quantum communication, where we can transmit information between two different parties. And it's very, very instrumental for cryptography moving forward with tools like quantum key distribution, where it's kind of interesting. I talked about how whenever you measure the qubit, it's either 0 or 1. Well, if someone tries to intercept your message and measure the qubit, they collapse the state. It's immediately known that your message has been intercepted. Now, with that entanglement, though, it has another key purpose here. Because unlike traditional bits, you can't copy a qubit. Okay? So we need some way of understanding what different states are at. But what we can do is instead of copying a qubit, we can entangle it before we begin doing procedures, and we know that they're entangled and they're in the same state.
So how the qubit representation look like? Whether have any specific unit or length of the unit?
Yeah, that's a good question. So for qubits, there we go. For qubits, I talked about how that alpha and beta are probabilities. Okay, whenever you have a series of probabilities, what do they have to sum? One. So we're always going to have it somewhere on this unit sphere. The qubit exists somewhere on this unit sphere because those probabilities have to sum to 1. Oh. Does that answer your question? All right, great. There we go. Now, let's go a little bit more into superposition and entanglement. First, I'm going to walk you through this image on the right. What we're saying is that, if you remember from chemistry or physics class, you can have let's say an electron around an atom. And it can be in its ground state, or if it gets struck by a photon, it can be in an excited state. Okay, but with quantum physics, you can say that it's actually in a combination of those states. It's in some alpha probability of being in the ground state and some beta probability of being in the excited state. However, like I said, whenever we measure it, it collapses. That superposition collapses, and it's either in the excited state or the ground state. Now, this is the power of quantum computing. So if I have n classical bits, let's say I have 3 classical bits, it can be in one of 8 states, right? 2 times 2 times 2 is 8. It can be in one of those states. If I have 3 bits, whatever the combination of those, it's in one of those states. With quantum computing, if I have 3 quantum bits, it simultaneously represents all 8 states. So with that simultaneous representation, that's where we get those advantages when we go to like hyperparameter optimization for AI, is that we can quickly determine what's going on there.
How do you decide what can be an N? You said
Yeah.
N qubit, right?
Right. Now, there's the side of that where you're going to be limited by the framework you're working on. How many qubits do you have to work with? There's also other limitations, where it's going to be based on your algorithm. How many do you need? But right now we're in the NISQ era, NISQ. That's noisy intermediate scale quantum era. In this NISQ era, the problem is that whenever a quantum particle interacts with its environment, that could be a measurement, or that could be other interactions from heat in the environment, and even just spontaneous quantum effects. Sometimes a quantum particle just, emits a photon and goes back to the ground state. We didn't do anything, but it just did that, kind of like radioactive half-life. We can have a probability for how often that's going to happen, but we just don't know. So with that, we have to designate some qubits for fault and error correction. So with these qubits, we have to duplicate qubits. So even though our algorithm may only require 8 qubits, we may have to specify additional qubits for fault correction, error correction, especially in the NISQ era.
You have any objective function if you do the some of the, for example, predictive model. We know that we want to increase the accuracy for the prediction, right? And then we try to learning each to the point. But in the the quantum computing, we may have one or more than one the task, or just handling about the one task and then determine about probability for the 0 and the 1 situation. So my question is, do you minimize the error rate? Is the objective of the two?
Yeah, so it's we can do the trade-offs, and I'm so sorry, it's left my brain. But someone came up with a handy formula for calculating how much error are you willing to accept, what probability that the answer that you get is the correct answer, and you can use that on how many times do you need to repeat the experiment, how much error correction, how many additional qubits, which are called ancillary qubits. They're not directly involved in the computation of the thing, but they're required for that error correction and for other procedures within the algorithm. And so
that's a video from one year research problem, but Microsoft recently had some new achievement.
oh, that's great.
Yeah, just Google it. They have a recent Nature or Science article about it. So you can do like a 20 quantum bits
Okay.
to achieve certain amount of accuracy.
Oh, that's great. That's great. I'll look into
Because
that.
right now, right, accuracy, reliability.
Yeah. Yes, sir.
I apologize. I don't have much knowledge, so
Everybody.
But when you said like how we figure out what state a certain qubit is, you said, well, we just got to entangle them and they're good. Should I treat entanglement as a state a qubit's in, or just an attribute a qubit has?
Okay. So a quantum particle, all right, we can use operations that I'll get to here in a minute to entangle it. We purposely make it where these 2 qubits are married. Okay, whatever we do to one happens to the other. Okay. And so whenever we measure it, they'll both collapse to the same state. Okay. And so with that, we can use that for various things. Like sometimes we need to make an intermediate measurement. Okay, and we can actually use that to purposely collapse another qubit. And additionally, so we can't copy qubits. Well, how are we supposed to transfer data in one algorithm?
We can force another one to be the same value as a qubit.
That's right. That's right. So instead of copying after we do the computation, we entangle them before the computation. That way, after the computation, we can forward another qubit. Does that make sense?
Yeah.
All right. Yeah. So that actually brings me to like superposition and entanglement in AIs. So that entanglement in AI is crucial for us to be able to do these repeated iterations. That way we can see what's going on. And then superposition, that's what allows us to do that hyperparameter search so much more efficiently. We can use Grover's algorithm with that to quickly test all possible values. Aha. Now, how do we actually do computation in quantum computing? So in classical computing, we're going to have AND gates, OR gates, NOR gates, things like that. But the same isn't available to us in the quantum world. However, there are some analogs that we have available to us. Okay, one of the basic ones is the poly X gate. We flip the state of a qubit. Okay, from 1 to 0, from 0 to 1. Now, all of these quantum operations, these gates, are fully reversible. That's a necessary function of a quantum gate. That if we do 2 knots in a row, we end up back where we started. Okay. Now, there are some other gates that maybe it's not one and then the other. Maybe you have to do 2, 3, 4, based on, you know, how much are we rotating the value by. That's what happens. All right. The Pauli Z gate, all right, is a phase flip. Okay. So with the phase, it's one of those dimensions on that sphere, that block sphere that I talked about. And so with that, we can use the Pauli Z gate to do a pi rotation on that sphere. Okay. And that becomes really important, especially like for search. We actually conduct search with quantum by, instead of sequentially going through everything, all right, we apply phase transitions with a function. And basically, it feels like magic, but by doing these phase transitions, the one that we want becomes 1, and all others become 0 by applying this function to those phase transitions. All right, now Hadamard gates. This is the bread and butter of quantum computing. All right, we talked about how crucial superposition is, but how do we put a particle in superposition? We got that electron in our ion trap, or whatever the case is, for that particle, you know, whatever it is that we trap. Okay, but that was interacting with the environment, right? So what we do is we apply a Hadamard gate, okay, which is right here, right? And all your quantum computing is being linear algebra. If you're physics, a lot of times you're more used to the ODE, PDE side, but for the quantum computing, we are linear algebra fans. But that Hadamard gate enforces that superposition. It puts these qubits into that superposition that we can begin our computations on it. And then we have a controlled NOT gate. The Pauli X gate is the NOT gate, but then we have a controlled NOT, all right, based on an ancilla qubit. That's an extra qubit that's not actually involved in it. But what we do with that is we're able to purposely entangle these qubits using the controlled NOT gate. All right. So with that, though, all of these gates are reversed.
We physically realize this case.
That's all right. So it's going to depend on your quantum hardware that you're working with.
Just an electron.
Yes, sir. And you know, this is going to be approximate. I've tried to focus on the quantum computing side, but a lot of times we are going to use magnetic fields to do twists and turns, but we just represent with linear algebra. I'll be honest, I don't know a lot about that physics side. If anybody knows more, I'd love to hear it.
Yeah, I'm teaching that.
Are you really? That's great. That's great.
I'm teaching that how to build a quantum gate.
Oh.
It's actually very simple. We know this for like 50 years. Physicists know this like close to 100 years.
Oh, yes, sir. All right, could you explain it real quickly, or is it not?
Well, like if you have a pure gate, pure state 1 or 0.
Yes, sir.
Okay, but that is basically referred to a particular direction.
Yes, sir.
And then we just need to apply a magnetic field with the right size, the right duration of magnetic field in the transfer state, then we can break it. In other words, we have a not easy. It is a quantum mechanics. If anyone take my class, if you will know it, it's a typical formal problem.
Okay.
How to make a pure state and mix it as into superposition.
Okay. Thank you very much.
Yeah. Also, we have actually UMTC has a lot of good things, and which is not fully being utilized. Like all of this stuff, we have a magnetic resonance, an NMR machine down in the basement, and there's a lot of quantum computing, simple experiment and stuff.
Oh, that's good.
That's great. That's great.
So the class is quantum mechanics class or?
Yeah, I've been teaching quantum mechanics, graduate level quantum mechanics.
Okay.
I'm teaching. I have this like this All this notation you hold here if you attend my class for first 2 weeks, you'll become expert.
That's great.
And also I'm doing some research using the doing imaging, use quantum state to do imaging.
Okay, that's great. That's great.
Entangled state to do imaging. So entangled state to do imaging, the thing is the most powerful thing is like if you are standing here,
Yes, sir.
we do not send light through you, we send it to some other people. Or we can get the image.
Oh, that's very interesting.
So that is a lot of applications.
Okay. Thank you very much. Thank you very much. All right, so I talked about reversibility. All these quantum gates are reversible. Additionally, that entanglement is necessary because we can't copy these qubits. Now, real quick, I'm not going to cover math very heavily in here, but just that you know, typically with quantum computing, we use the Dirac notation where we have bras and kets. And I really like it because you kind of get away from what orientation is this vector in. If it's a ket, it works with this matrix. If it's a bra, it works with the same matrix from the other side. So it's a nice, convenient way to operate on this. Now, in AI. So I've touched on this briefly, but let me touch on it a little bit more. Okay, is that we have the instantaneous hyperparameter search. Okay, there's something called Grover's algorithm. I tried to get a GIF to load in this PowerPoint, but it just wouldn't work. But there's a lot of good visualizations and videos out there where they use rotations to correct for the error to find it. It looks like magic. That's I watched the video the first time I saw it like 10 times. But it's also really good for that complex optimization. Okay, whenever you're facing these problems that have the combinatorial explosion of possibilities to search, that's where quantum AI is going to shine. And then high dimensional data processing with entanglement and superposition. Like I said, we use these principles, we're able to do that massive search. Now, all right, quantum computing is not better than classical computing in every instance, especially in the NISQ era. Okay, we are not going to want to use a quantum computer to process our data. It's no more efficient, okay, and it's much more expensive. So what we're gonna see, I think, especially for the next decade, is the hybrid approach. We're gonna let classical computers do what classical computers are, all right? And since these quantum computers are so rare, we have so few qubits, we're gonna pass the essential, say, hyperparameter search to a quantum computer, they're gonna give us a result, we're gonna bring that back. So it's going to be this hybrid approach where we try to use each modality for what it's best for. Current applications. Every time I search it, there's another one. There's another company. There's another person doing a great thing with it. One qubit is doing pattern recognition for portfolio performance. Tom and Dr. Lee did some stuff with that over the summer. Okay, where they're using quantum AI for financial planning and pattern recognition. D-Wave is working with, so whenever you're talking about like logistics and supply chain management, you know, we learn about like the traveling salesman problem and stuff. Those are complex optimization problems. What is the best way to move this material or to, you know, connect these things for maximum efficiency? That's another great thing for quantum. You have Protein Cure as well as Microsoft working on some drug discovery. Okay, and that's probably going to be something I end up in with graph neural networks, like molecules of little graphs. Then CQC is actually doing a lot of interesting stuff with natural language processing. Okay, whenever we're dealing with these huge vector spaces, that's a great space for quantum computing. And then Toshiba on the like cryptography side, they're working a lot with the quantum networks, you know, where we can apply that quantum key distribution and quantum communications, because quantum is going to simultaneously make our cryptography so much more secure, but it's destroying our cryptography. Whenever we have things like Shor's algorithm, Grover's algorithm, where we can quickly factor prime numbers, that kind of tears up our current. There's some approaches where they're like, oh, this will be better and things like that. But I see probably 10 years from now, when you're talking about governments or militaries or even large corporations, they will not transmit their data on anything except for quantum.
could you focus more on drug discovery?
I'm sorry.
Drug discovery, protein cure for drug discovery, you said.
Yes.
Using that in this field?
Yeah. They're working with it right now. They have some published results. So it's one of those things. I haven't dove deeply into it yet. Okay, but they are using quantum to do optimization for drug discovery right now. If you join my Discord and stuff, I'll try to post that article. Okay. So, I mean, we just went over the basics today. All right. What is a qubit? What is superposition? What is entanglement? The gates. We're talking about how it can be applied in AI as well as some current applications. And I mean, moving forward, these quantum computers are rapidly getting better. It's going to become a central tenet of the leading AI in the field. All right, now we just have discussion. What do y'all have?
So my question is, definitely we have a benefit versus some cost associated with quantum computing, and then not all the application maybe need like quantum computing, right? So from the observation learning and then whatever knowledge you have, what do you see? Which kind of problem maybe is good for the quantum computing?
So with quantum computing, we're going to want to give quantum computing tasks where we're processing multiple states at once, all possible states of a problem is key. That's where we're going to find those advantages. As like I said before, all right, our best quantum computers right now have a little over 1,000 qubits. Okay, they cost millions or billions. Okay, there's not very many of them in the world right now. It does not make sense to process all of our data on a quantum computer. So especially in this NISQ era, it's really important that we reserve the quantum computer for the most essential parts that have that optimization where we're trying to search many values at once. And also with this NISQ era, we have to have those Ansel qubits for error correction. And we have to have a certain certainty because quantum is going to be non-deterministic. We're going to have to repeat it several times because we don't know if we had a particle go to a ground state. We don't know if there's noise and interference from the external world that disrupted our computation.
So you also say about optimization and efficiency is the most good benefit, right? So this technique can apply to some real-time applications?
Yeah. This is me hypothesizing. I haven't read specifically on this, but depending on the scope of the problem, I would say definitely. If you had a well-defined problem that you could process on current quantum computers, I could see that being a key application for routing or forecasting with. Now, the problem right now is that we're in that NISQ era. How many times do we need to repeat this? How many qubits do we need to process this?
Okay.
Good. Yes, sir.
So, well, kind of two-parter question. One part is like, for like practical learning and how to play with these things, there's no like, I'm guessing there's no like simulator or anything.
Oh yeah, there's a bunch. There's a bunch.
Okay.
Go to IBM, go to Microsoft. They're dying to learn. For this material, I'm working in Qiskit. All right, that's IBM's platform, Qiskit. Okay, now it's one of those things I thought they're deliberating on which platform to go with. I went with Qiskit because they have tools for all those. Or we're touching quantum bits to a higher abstraction AI where you don't want to do machine code for AI level tasks. Okay.
Oh, sorry.
No, go ahead.
So those like simulators more like I think like the it isn't like TensorFlow playground. It's actually kind of like run code through those type of simulators. If you're saying,
yeah, they do have simulators and stuff. You have to realize that with quantum, the reason quantum is advantageous because it can do stuff that takes us forever to do on classical computers. But they're still really good. They're very interactive. They're hands-on. They walk you through the process. They walk you through what's going on. They show you how to use their software.
So second part question then, if someone wanted to make a startup or a company, what would be the best way to go about that? Would it be try to go for a cloud solution with these companies, or would it be like maybe working with UKC? They would like allow that if that's even possible.
Yeah. So on that, right now, the best quantum computers are going to be in the hands of these giant corporations. Okay, but we're starting to move into an era where we'll be able to ramp time on those. So like right now, that's a really good question. And like any business venture, it's come up with an idea and see if it works.
They're like, there's no like minimum like try to even attempt that. So I was like, I had an idea. I could probably do something with NLP to make better flirty messages with quantum computing. Would I go to like an IBM or
Yeah, you have any thoughts on that?
I will chime in a little bit. For generally comparing quantum computing, general CPU, GPU computing, like most linear algebra related algorithms are slower. If you use it using simulator, let's say Fourier transform. Right? So there is a quantum version Fourier transform, QFT, which is the core of the show algorithm, the big thing of the show algorithm for regular. So it is slower if you simulate it in a general regular CPU, GPU. But for certain areas, people call it sweet spot. For very complex problem, for example, very famous problem, where quantum computing is much faster than traditional computer. So there are so-called sweet spot or something for a particular problem. But
So a question.
For those big corporations, they build their own quantum computers. Do they allow general access?
Yeah, I know with Microsoft especially, I believe IBM as well, that you are able to run programs using their machines. Now, I think it's largely, I haven't been pricing on it or anything, but I know even as a learner, you're able to access those machines for some basic operations. Yeah, I don't know it offhand. I'd be happy to share that with you, but I do know that Microsoft especially does have some use cases for that. And I know that reading on it, there are some applications, especially for institution level access to those machines. Like,
Have you used any of those truly quantum computing?
so far I've just been playing with simulators. I'm still learning and progressing myself. Like I said, I'm learning it and teaching it to you guys a month later. Yeah.
Now that in the computer science community, most work are done on the simulators rather than real quantum computing.
Especially really good because this section is not only about the seminar, but we have some of the hands-on. So next time we can give some of Jupyter Notebook. Everybody can try it before you're coming and then ask more questions. We think that may be good. We share the PowerPoint presentation together with some Jupyter Notebook, and anyone who does some of the exercise and coming back here as challenging.
There we go.
And then also teaching.
There we go. Yeah.
So you mentioned that these ones appears to area over time.
Okay, so it's not so much the quantum computers deteriorate over time, or at least not as opposed to any other mechanical device, but it's that noisy intermediate scale quantum era. We have to protect both from quantum noise and classical noise like heat and interaction with the environment. Okay, so it's that our qubits become less reliable the longer they exist, it's called coherence time. And that's one of the big research fronts that not only they're trying to increase the number of qubits, but the issue there is how do we do that while maintaining long enough coherence times to do the calculations?
Yeah, I can answer better the question by the coherence. Can you show your first slide?
Yes, sir.
Show some things. I can explain it. Yeah, this is, you know what that is? That's called dilution refrigerant. It's just like air conditioning, but in the simple language. However, that will can cool the temperature to 1 millikelvin, 10 to -6. So why do you need to have that temperature? It's exactly because of the air. At that low temperature, there's a very, very minimum noise. So the quantum computer can work. However, I have those things which I have worked in my lab. Run it is extremely expensive. Now I cannot polish. So then the IBM and Microsoft and maybe Google, a couple other places, can have the financial resource to build that and run it. Yeah, but I think scientifically, eventually for quantum computing to become widely useful, I think that we need to have that many more.
Yes.
So it will be useful for people, for computer science students, to know how that thing works.
Yeah.
Not how a simple like superconducting people conducting junctions, and how do you trap atoms, at least conceptually know the concept, how to manipulate spins.
Yes.
So in terms of quantum gate design, we have to design ourselves, or is there some of the predefined?
Yeah, no, you can operate at whatever level of abstraction you want to. There are machine learning platforms
Yeah.
for either based on programming language like Python, as well as there's several that have their own custom machine learning, where you get to operate at that level of abstraction, machine learning, and they handle the qubit side on how to, how is this application of gates and stuff.
I see. So we don't have to manually design the underlying.
Right. The space for that would be if you're trying to design a new algorithm or a new approach
Right.
or a different combination based on what that quantum computer is capable of. So it's going to be a case where for common tasks, they'll have that level of abstraction, but it's still an area of active research. So depending on what you're focused on, you may have to dive into that quantum level to develop your own algorithms.
For something in machine learning, like backpropagation, where it's like you have to make changes at each like layer, how would quantum computing like be useful in something like that, where you still have to kind of work in a linear fashion?
Yeah. So with that, I mean, for each input, even in traditional machine learning, you can represent that as a function. And what we're trying to do is approximate a function using a series of linear operators with machine learning. Okay, so with quantum computing, that's that space where we are able to use things like Grover's algorithm and Shor's algorithm, where we can pass all those inputs. So while very similar, quantum AI likely will not use the same architectures we're used to. Okay, there's been attempts as well to just kind of replicate the structures we're used to. However, I suspect that we can better apply the algorithms for testing all of these inputs as opposed to the series of weights that we're used to with machine learning. Does that answer your question?
Yes, it does.
Thank you.
So is that why you specify hyperparameters? Because like you're not specifying, we haven't made a system yet, because right now our layers are linear versus the quantum architecture that could pop up later on. Hyperparameters, you're saying hyperparameters because then you just take that linear structure, do that a few times that way, but the structure itself, we're going to figure that out later for quantum computers specifically, maybe.
Yeah, from AI side, it's so difficult to go to the quantum framework and building up the community. Right? That's why what we did is bring the quantum layer to the current neural network. One of the layers of quantum network. And Tom did it for his own problem. So we see that some improvement to the quantum layer, but not entirely designed this open.
So for machine learning, you are saying basically we are using quantum computers for data processing, right?
So you can apply some different level. I think we definitely see that some of the improvement in some of the layer in the final layer. Near to the classification problem, another project we applied to the low layer, since the data can be already optimized and the learning can become more effective. I think you mentioned that efficiency is one thing, optimization in the hyperparameter optimization or reduction of the computer side, and learning can be more effective because of the receipt advantage of two and then layer to the GANN is one of the GAP is one of the, and we also try to support getting architectures between the two and then.
So it's basically like we need to research more about how to modify the architecture to introduce computers.
Right. So we do the PyTorch based one and the Python based coding, but we only bring the quantum layer to the one of product one. I think that that's a small step.
Yeah.
I could go to the two and then quantum layer.
And the level of this is a little bit beyond just introductory session stuff. Take a look at QAOAs and variational quantum eigen solvers. You'll see that these are used a lot in machine learning. And so we're at this stage, the level of quantum computers we're at, we're not going to try to insert an entire model into a quantum computer. That's not where we're at right now. Did you have something?
Yeah, I'm just curious, when you work on the quantum computing simulator, was simply constructed. Yes. Let's move there.
So, I will say that, a lot of the simulator is learning based, where we're not running a full quantum algorithm. So I suspect that, many of the solutions are stored. Okay, at least at the learning level. Okay, to where, hey, you can play around with Shor's algorithm or Grover's algorithm for this set of inputs. You can store the outputs, but you can still play with it to understand how it works. And that's the thing with quantum computation. If we could simulate on classical computers, we would maybe quantum computers. But at a basic level, either we accept the computation cost, where like, hey, the real-time computation for this is n cubed, but hey, we limit you to 10 qubits, we can calculate n cubed on 10 qubits.
Simply a software package that produces space.
Yeah.
Machine.
Yeah, IBM has Qiskit.
Do you know anything about it behind that? What is how they do it? I'm just
No, I don't. I'm sorry.
it all involves software. Basically, that was built, constructed based on the conventional computing
Yeah.
algorithm.
Right. And I mean, with quantum computers, you're going to have classical computers and the equipment, performing the operation.
Simulated.
Yeah.
Okay.
All right.
So time, I think we're done.
Thank you, everyone. Thank you. I'm sorry.
You get the information about the.
Yeah, hey, if anyone came here for Dr. Loeb's class, I believe you're providing some credit if you sign in. My notebook over here, if you haven't signed in, please go ahead and do that. Additionally, the reason I'm doing this seminar, I think quantum's really cool and I want smart people to work with. Okay, so if you would, just take a picture of this one way and we'll post and share there. I'll provide all my materials there. Let's do some cool stuff.
Or you can email me.
Yeah.
While you and share the video with you before the second seminar. Many recommend.
Congratulations. Thank you. Thank you.
Write down my email.
Thank you.
Yes.
Very good.
Thank you.
So you
Good luck.
No, I haven't been in physics.
Okay, all right.
If I had limited time.